Hello everyone, welcome to third lecture. So before we start, let me advertise our new contest. So we have JetBrains contest. It's called JetBrains Youth Challenge. We had it for the second time. We have it this year. It will be on. So they have two tracks: math track and coding track. I am in charge of coding track, so I mostly talk about coding tracks, but if you like math, you also can join math track. It also will be awesome. So coding track will have only one contest, and it will be on where the timeline on November 24th. So it will be like normal coding round like you usually do. So if you like this thing, you always like this thing if you join this club, so you can register here and take part in this competition. It will be fun. So I will prepare the problems. Not only me, but I will be like the head of the team who will be preparing the problems, and we will prepare a very nice problem, I promise you. So what we have today, we have 8 problems. Let's look at the standings. Standings are pretty fine. So a lot of people solved first 4 problems. That's really good. If you didn't solve the first 4 problems, it's also not bad. Okay, if you solve third problem but not fourth, it's kind of strange, but we'll talk about this. Good. So these problems are actually difficult problems, especially these 2 problems. So we'll talk about this later. So let's start from the first problem. So the first problem is really simple. So again, you need to read the statement, understand what's going on. And what's going on here is we have some rules of some strange. It doesn't matter what is competition about. The matter is that we have a tournament. So we have a tournament with n participants, and there are some rules that explain how this tournament. It's like normal system when you have 2 power n, 2 power k participants. Okay, so if we have some number of participants, let's have how many? 6. We pick the maximal power of 2, split that many power of number 2 such that they can compete in the current. Half of them passed again. Okay, so we pick maximal like 4. Build these pairs. So these two participants compete. One of them is eliminated. Then we have less participants, and then again we have 4 participants. We split them into pairs. Yes. Yeah. Again, they split into pairs. Some of them are eliminated. Some of them, and so on. In that we have only one winner. So yeah. So we have some tournament system. It actually doesn't matter for the rest of the problem, but again, it's good to read the problem statement and understand what's going on. So we have some tournament system, like normally you have some number of participants in the beginning. Every time you have some rounds, some participants are eliminated, some go to the next stage, and in the end we have only one winner. Good. Now let's move to the problem. So what we actually need to calculate. So we have need to calculate total number of bottles and total number of towels. So we got about 2 numbers. So what is bottle? What is towel? Let's look at the bottle. So each match needs B bottles. Okay. Again, number B is just given you to complicate the statement. It doesn't get so we just need to calculate number of rounds, because number of matches. Yeah, because every match will need B bottles. So we just calculate number of matches multiplied by B, we get number of bottles. Yeah? So it's simple arithmetics. So how to calculate number of matches? No, you see. So every match in every match you eliminate 1 player. Yeah. So it actually doesn't matter what tournament system you have. So if you have matches of 2 players, every time you eliminate 1, the number of matches will always be n-1. Or if you like trees, yeah. So if you have a tree, binary tree, so every node has 2 children, then number of internal nodes is equal to number of leaves minus 1. Yeah. Because of the same reasons. Yeah? Yes. Every time you have an internal node like this, so I'll just mark all the internal nodes for you. So every time you have internal node, you kind of increase number of branches by 1. So number of internal nodes is always n minus 1. So the first number will be always equal to n minus 1 multiplied by b. That's all. And then you just check again what you do. So when you think the problem is actually easy, that these formulas, before you start programming, just check it for the given examples. So in the given, you say 5 and 2. Yeah. So I need to multiply what? Doesn't work. No, this just doesn't work. Okay, so it's something. What have I missed? We built for each participant, and one for a dash. Okay, not by b. So every match I need 2b plus 1 bottle. Okay, and that's again about how important it is to read the statement. So again, that's good. So I catch it before I start programming. Good. So before I start programming, I write down my formula and check if it satisfies the examples. So in these examples, I have n equal 5, b equal 2. Okay. So I have n minus 1 is 4, and 2b plus 1 equal 5. Yeah, so you have formula multiplied by 5, it's 20. Looks fine. Yeah. You can also check the second statement. I will not because I'm lazy, but in the contest you can check both statements, or both examples, just to be sure. What about the second number? Second number is number of towels. P towels given for the whole tournament. Easy. So each participants, I have n participants. Each needs p towels. So this is just the second number. You think, okay, maybe it's not that easy. Let's check. So you check that 5 by 3 is 15, 8 by 4 is 32. Looks fine. So that's all. That's the whole first problem. You just read the statement, write down the formulas, implement. You did it. So that's all. No tricks here. Just careful implementation of the two formulas. Okay, I'm not sure which. If you missed the first problem, maybe the statement is too complicated. Again, it's okay. Statements are made intentionally made overcomplicated. So people write statements, so you need to just invest some time and read the statement and understand what's going on. That's not bugs like a feature. Yes. So authors specifically make statements so you have to spend some time reading them and understand them. It's part of it's actually a big part of programming it also. So if you start working in some company, so this a lot of time you will be doing not writing the code but reading some strange texts. So you need to read the text, understand what the problem is, then implement this problem. That's actually problems like this actually prepare you for your normal programming life. So it's not a bad thing. So that's what I'm trying to say. Yeah. So if you feel like you're frustrated, or if you feel it's boring to solve this problem, it may be. But it's after you do it several times, you kind of used to it, and you don't spend that much time doing it. Yeah. You quickly read the statement, quickly understand what's going on, implement, submit, get accepted. You're done. Okay. You move to the next problem. So problem B, well, again, it's kind of easy problem. So again, you need to understand what's going on. What's going on really is a simple thing. So I have a street. I have the houses near the street. So odd numbers go on one side, even numbers go on this side. You even have a picture. So authors are that kind to you. So they give you the picture so it's easy to understand. Sometimes authors do all the same thing. So they explain it in the text, but don't give you the picture. So you need to spend some time drawing this picture on paper. Here, authors are very kind. So they give you the picture so you immediately understand what's going on. Now, what you need to calculate, again, it's just minimal time. So you just need to calculate time. The car on the left should it takes for the car to the left to get to house number A. And so it's actually given this picture and this string, this line should be enough to understand what's going on. You don't need to read all this text, but you have to read all this text. So if you're in the contest, you always need to read this text. But what would I do in this contest? So if I see problem like this, I see this picture, I see this line, I immediately start to code, and then maybe I'll check the examples. I would not read this problem until I have wrong answer test 3. So if I implement this task and have a wrong answer test 3, then I will go and read this text, because text is long and this picture kind of explains everything. So that's nothing to tell about this problem actually. So what we need to do, we need to calculate the distance between the left border here and the house number A. And you can read the state. So if I have n houses and I'm looking for house 2, then I have 4 houses. I have 1 and 3 here, 2 and 4 here. So number 2 will be here. Yeah. And distance to this house is 2, because I'm standing here. It's 1, 2. Implementation is quite simple. You look at the number, see if it's odd or even. If it's odd, you calculate distance here, like divide by 2. If it's even, you calculate distance by t, like divide by 2, and it's n minus this. And nothing really to say about this problem. It's just pure implementation. You look at the picture, maybe read all the statements. If you're not sure, then read all the statement, and then make a simple code that checks if number is even or not. Let's check someone who was fast, who was really fast today. You. 5 minutes. Okay, so it's even 3 minutes. So it's 2 minutes for the first problem. Okay, and 3 more minutes for this problem. Nice. Yeah. So that's the whole. Let me back. What? Why? Okay. No, you can do it like this also. So if all numbers are small, okay, you can just move one by one. Okay. So you start by having houses 1 and n, and then you move one by one. Every time you increase this number by 2, decrease this number by 2. Okay. Also, okay. Yeah, but that's how you solve problem in 5 minutes. You don't overthink. If you have solution and you think it works, that's what I would expect. So that's how I would implement it if I would. Yeah. So you look at the number, check. So a and 1 basically checks if number is even or not. So you bitwise end with 1. If it is even, then last bit will be 1. If it is even, last bit will be 0. Then you make not. So this checks if number is even. So if number is even in the second line, the answer is like this. Yeah. A plus 1 divided by 2. Why not? So what we have in problem C? In problem C, we have actually quite so this problem occurs in multiple different forms. Basically, what we need to do, we have some objects, and we need to find 2 closest objects by some metric. So different variations of this problem are well studied. So there are some specific algorithms for this problem for various different. Like if you have points on a plane, people know how to do it like in log n time or so on. And here we have very simple version of this problem. So we just have points on line, and we need to find 2 closest points on a line. Yeah. And the way you do it, so again, you just let's write the picture. The way you do it basically, so you have a line. You have a line, you have some points. So closest points are always neighboring points in this. So you can, if you sort all the points by this coordinate, you just need to look at this difference, this difference, this difference, and find the smallest one. Like here I have. So if you sort all the elements, you have -3, and then you have. Do I have enough space? I have enough space. You have 0, 4, and 6. Quantity of pairs to distance. Okay, you also need to calculate how many pairs you have. Yeah. So you sort all the numbers, calculate the differences. I have difference 3, difference 4, difference 2. Find the minimal one, and then calculate how many minimal differences you have. You can do it in 2 swoops. You can first time you calculate the minimum, and then you calculate how many elements equal to this minimum. Yeah. So again, you moved from this array. So again, let's full part works like this. You have your initial array. Let's just move in small steps. So you first sort this array. You have array like 3, 4, 5, 6. Then you calculate differences. You have differences is equal to 3, 4, and 2. And then in this final array of differences, you find the minimal element. And if you have multiple minimal elements, you just calculate how many minimal elements you have. Pretty standard, actually. So all the steps are pretty standard. Okay. Let's check what you have. What's your handle? It was I remember you asked last time. Yes. This you, right? No. No. Okay. So yes, good. Yeah, I really good. I finally remember something. Usually very bad at names. So let's look at your code first. So should I check all of them? Or just okay? Let's check all of them. So here you just output too many elements. Yeah. So just obviously just forget to remove this debug input. So here what we have. Answer as well. No, that's okay. 2, 0. 0 is not very good answer. So if you have 0 pairs with good answer, it doesn't look good. So why you have this problem? Why number called 2? Why is it 2? You just you maybe misread the statement. You think the difference is always 2. No, it's not always 2. Okay. Let me check all of them. Let's check all of them. Now finally you implement something that let's work on big. So now if we have big test, you have memory limit. Why we have memory limits? Let's see. Okay, that doesn't look good. So you check all possible pairs. Number of pairs is like n squared. And for these constraints, we have like 10 power 5 elements. Yeah. Again, you can just look at it. So we have 10 power 5 elements. So if you look at all possible pairs, we have 10 power 5 multiplied by 10 power 5, divided by 2 doesn't matter. So it's like 10 power 10. 10 power 10 is too much. So normal processor is like here, like several gigahertz. Yes, so it makes about billion operations per second, simple operations. So for competitions, you can like it's like more like 100 million operations per second, something like maybe several hundreds of millions. So 10 power 10 is like 10 billions. It's too much. It will take like 10 seconds at least to fill. So yeah. So if you see constraints like 10 power 5, usually it will not be an n square solution. Sometimes it actually will, but usually it's not n square solution. But you I like how you move from upgrading your solution from that. So you start with one solution, find the problem, write another solution, find the problem. Okay, so then you fix the memory limit and then you fix the time limit. Good. So let's look at your final solution. Is it ChatGPT or not? Usually ChatGPT makes these comments. Just be honest. Is it your solution or ChatGPT? Because it's very different from your solution. Don't use ChatGPT to solve the problems here. It's never interesting because ChatGPT right now solves easy problems pretty well, especially this problem. This problem is kind of standard. So again, it uses very standard operations. So it's quite good solving easy problems right now because basically it learns how to solve all easy problems. But that's okay. If ChatGPT solves problems better than you, that's not a good sign. Okay, it's probably a sign that you need to study more because it became much interesting when you reach the problems that ChatGPT can solve. So if you solve problems that ChatGPT can solve, it means you will be replaced by artificial intelligence. Yeah. So try to learn how to solve problems which ChatGPT cannot solve, and then you will kind of reach the point when you will not replaced by artificial intelligence pretty soon. And still probably will be replaced, but we will be replaced. But maybe we will delay this point at least. So again, let's look at your solution. Last solution. So again, your solution is pretty close to actual solution. Is it still ChatGPT or not? Okay. Which solution is actually yours? Not. Okay, maybe this is yours because it doesn't have these comments. So this solution is actually pretty fine. Besides that, we have these two loops. And again, so what we need here, we need to understand that the minimal difference is always different between two closest elements. Another popular problem is actually finding the maximal difference. So how to find the two farthest points? So if you want to have two closest points, you sort the elements and check a difference between consecutive elements. And if you look at the maximal difference, that's difference between the leftmost element and the rightmost element. So if you need to not minimize but maximize the same value, you look at the leftmost element, look at the rightmost element, and find this difference. So like one-dimensional problem is pretty easy. My code don't optimize. Oh, that's actually. So it's not bad that you use ChatGPT. So you obviously need to learn how to use ChatGPT for your future life, because it will be with us for a long time, and maybe it will be even much smarter than it is now. But just for contest, it doesn't make sense, because we're not competing of who is better with interaction with ChatGPT. We want to learn how to solve these problems using our brain. Yeah, that's like what this contest is about. So if you use ChatGPT, it will be just different kind of contest. It's also maybe interesting contest of who is better of using ChatGPT, but it's like different type of contest. Let's look at your solution. Wrong answer, test 6. So test 6 actually must be something interesting. So we read the array with that minimum list of 15. But again, here you have tools. So you have wrong answer, yes. But it will be, even if we fix this wrong answer, it will be time limited, because we have these two loops. So we have n square time solution. It will just too slow for this problem. But you just reach this wrong answer before you reach the time limit problem, because it doesn't work on small tests. So we have this small test, and even here we don't work. Minimum of temp. Oh yes, no. Here the problem is because you didn't sort the numbers. You check here. No, you do something strange here. So let's see. Temp is minimum of temp and if and count equals 0. That's not how we do it. But that's okay. If you want to do it like this, let me show you. If you want to do it like this. So let me explain what we're doing here. So what we're doing here. So here we're trying to calculate two values: minimal and count will be number of these minimums. Yeah. So temp is just temp. When you change, here's change. Okay, let's first find the problem here. Then I will do it. It's just overcomplicated. I won't just change it, but okay, let's read it first. let's say minimum is this, minimum of temp and this. Then we check if this equals to temp and count is 0. How can it happen? Count must be always never 0. How can it be 0? Okay. Why is it 0 here? Let's check this. If minimum is not temp, so I updated my minimum, and temp equals this, it must be equal to this. I think here it must be 1. I think this is the problem. Okay, let's just try this, and then I will show you how to write the same thing, but more simple. Okay, let's spend some more time on this problem, because this problem is actually important. So it's again, it's one of the classical problems, because it like variations of this problem occurs in. So how do you do this thing? So I need to calculate again. I want to calculate two things. Yes, I'll calculate this minimum and this count. Let's write a normal code. I don't want these two loops, so let's just rewrite it. So I'll just replace this. I will sort them. And here I'll just remove one loop here. Up. And here I only check difference between two consecutive numbers. Yeah. So let's look at difference. So let's look at this. I don't need the stamp. No, okay, let's. Is it long? I think we have. Let's do it like this. Like this. I don't need that. So I know this value is greater than me. I plus 1 minus I. Yeah. So now here I will do some very standard trick. So what I want to do, I want to update these two variables. Yeah, I want to update minimum and count of minimum. Yeah. Okay. So okay, let's write it. Let's try several variants and then we'll optimize it. Okay. So there are several options. So if this temp is greater than my current minimal value, less. So if temp is less than my current minimal value, it means strictly less. Yeah, it means I need to update my minimal value. So I say my minimal value equal this temp, and count equals to 1. So I found new minimum. Now I have one minimum. I discard all previous minimums because they are worse than my minimum. My new minimum is better. And just as a counter now. And they say else. If my element equals to minimal value, then I see I don't update my minimum, but I see new element equals to my previous minimum. So I just update the counter. And you don't need this. That's all. That's how we do it. Another way of doing the same thing. So this I actually prefer because of reasons. I don't know. I see like this. So if so if my new minimum is better, I will just update the minimum and discard all previous elements, and then if like this. So I first update minimal value. If it is updated, I just clear the counter, and then I just update it like this. I prefer this probably because here is simple problem. So I don't like this one. So this one is like you initiate your counter with some value. So you kind of you process all minimal elements differently. So you process first element separately. Here I just clear the counter. Clearing always easy. And here I process new element. So here maybe something. So in another problem here must be some different operation. Yeah. So I may not calculate like a number of minimums. I may calculate like minimum and another statistics about this minimum. Yeah. So here maybe something more interesting than just plus plus. So I think this is how I usually program it. This code is actually also absolutely fine. Let's check it if it actually works. Maybe I'm wrong. Yeah. Sometimes I make mistakes in programs. No, it will work. Okay. Okay, that's problem C. Any more questions? Okay, so again, this problem of finding two closest points is very standard. So for one-dimensional case, you just sort all elements, find the minimal difference between consecutive elements. For two-dimensional case, it's much interesting. But in one dimensions, all these problems are very easy. Good, let's move next. In problem D, we have very complicated statement again. So statement is describe you something strange. I have some airports from 1 to n. So let's look at A, and B, and so on. You have some strange rules for flying. But actually, when you read it several times, it is quite simple. So I have some airports in a line. So the distance between two airports is like module of the right. So like here. So this is the distance, and they say that all the airports belong to one of two different companies. Yeah. So we have two companies. This word two is actually important. So I have two companies, and all airports are split between the companies. And I only pay this amount of cost, yes. I only pay this amount of money if two airports belong to different companies. And you need to find the distance between first and last element. Easy. No, again, how to solve this problem? No, again, you start by thinking how this optimal path look like. So you start in airport A, finish in airport B, and then you have some intermediate airports. So if A and B belong to the same company, like company 0 and company 0, then you can just go from A to B and pay 0. You can't get less than 0, so 0 must be minimum. If they belong to different companies, then your route should look like this. So you have some elements. So let's say you have some, then some 1, then some zeros, then some 1. If you have a route like this, no, it doesn't make any sense to have several transitions from 0 to 1. Because if you transition from 0 to 1 and then from 1 to 0, you can just go immediately here and spend 0. Even more, so if you look at the last 0 in this route, you can immediately go from here to here by paying 0. And the same with the 1s. So if you have several 1s here, let's have several 1s. So you can start from here and immediately go to here. So actually you pay only for this one transition between 0 and 1. And now the problem is actually very simple. So I need to find minimal distance between 0 and 1. But minimal distance between 0 and 1 is always 1. I always have neighboring 1 and 0. So that's all. So again, I claim that the answer is always 0 or 1. If A and B have the same color, have the same company, then answer is 0. If they have different companies, then I need to make at least one, so answer will be 1. So again, overcomplicated but really easy problem. So statement is complicated, but problem is actually really easy. Let's look at the solution. That's right. That's the whole solution. So I check these two elements, check if they different. Okay, C++. Okay, you can do it like this. So you check if elements are not equal, you have Boolean value 0 or 1. If they are not equal, then answer is 1. If they are equal, answer is 0. Okay. That's how people write in C++. Okay. Have something. Okay, that's more like it. Okay, so like more. So it's the same, but for normal people. Yeah. So we check if they're equal, we output 0. If not, output 1. No, again, this tricky problem. It's tricky problem. It looks complicated. It's actually need some thinking. But when you so some problems need a lot of thinking, and then implementation is simple. Sometimes problem is quite obvious what you need to do, but you just need to implement it carefully. You kind of need to learn how to solve both types. Sometimes you have something in the middle. You need to do some thinking and then some implementation. Okay, now we move to actually hard problems. So first 4 problems were actually not that hard, I think. But last 4 problems are actually interesting problems. They all require both some mathematical analysis and programming is not that easy. So problem E. What we have in problem E? First, we have very scary looking problem statement. So we have some strange language with bitwise operations. So you need to learn how bitwise operations works. So if you don't know how bitwise operations works, okay, I will not explain it now, but it's the way we do it is just by apply logical operations to all bits of your numbers. Here I have small numbers up to 10 bars. So I have 10-bit numbers, and just apply some bitwise operations. Yes. And what you need to do, you need to simplify this program. So you need to replace all these commands by some another commands, and you need to minimize. You don't need to minimize. No, you don't need to minimize. You need to make at most 5 lines of code. It's actually easy to minimize it as well, but not today.
Mom. Sorry.
Okay. I have two laptops. What I was talking about? Yeah. So how to solve problems like this? Usually when you have some bitwise operations, you kind of wanna take a look at each bit. So what happens to each bit? Here, sometimes you have bitwise operations and some more operations. So if you have not only bitwise operations, but bitwise operations and some arithmetic operations, like you need to calculate sum of some bitwise operations. So A and B plus A or B, something like this. Yeah, then it's more interesting. But if you have only bitwise operations, then they kind of applied independently for each bit. Yeah? Let's look at the first one. So imagine you have some here. I have here. Yeah. Let's look at the first test. So what I have some bits. So I have I have 2 bits. Yeah. So we have bits. Like that. Okay. I just went how numerate. Let's enumerate bits from right to left, like we usually do. So I have bit B, like A0 and A1. No, bits usually enumerated right to left because of reasons. So here I have the lowest bit, yeah, and and from 0. So this multiplied by 1, or by 2 power 0. This multiplied by 2 power 1. So you have your initial number A. Yeah. So what I'm doing here, I make OR with 3. So I make this number and then make OR with number 3. Number 3 is like 1 and 1. Let's add third bit because it's okay. It's just bad example. Do we have better examples? No, we don't. Okay, let's use this. Let's add third bit. This multiplied by 4. Yeah. So you have OR 3. What does mean OR 3? I'm OR my number with number 0, 1, 1. Yeah. This is free. Yeah. 0, 1, 1 is free. In binary. Yeah. So if I OR these two numbers, what's happening? So again, if you never saw this before, that's how you apply OR operation. OR operation basically does the following. If my number is 0, then 0 or something is this something. Yeah? No, like 0 or x equals x. So this bit will stay A2. So this bit will stay the same. And if you OR with 1, you will have 1, because 1 or x always equal to 1. So after you apply OR 3 to these numbers, you have A2, then 1, then 1. Let's use another example. This example is boring. Let's make OR. No, okay, let's do that. I'll just add some more operations. Okay, now again, you apply OR 3. Now after this operation, you have A2, 1, and 1. Again, you look how to apply this operation to every bit independently. Yeah. So all these operations are independent for every bit. Now you apply second operation, XOR 2. Let's see, XOR 2. 2 is 1, 0, 1. Yes. So if I apply XOR, I basically flip all the bits. Yeah? So you flip all the bits which have 1 here. So anything XOR 0 is this anything. Yeah. 1 XOR 1 will be 0. 0 XOR 1 XOR 0 will be 1. Yeah. And then you make OR 1. It's such a boring thing. Okay. Now I make OR 1. 1 is again is 0, 0, 1. So again I have A2, 0, and 1. So you just apply these operations. So if you start with these 3 bits, in the end you have these 3 bits. Okay, now let's look at some. So what can happen to a bit? So if you start with bit x, what can you get in the end? No, there are not that many options. If you start with x, so what bit you can have in the end? You may have the same bit x, yes, if you don't do any operations, or if they cancel each other. You may have bit not x. You may just flip this bit using XOR. Yeah? You may flip this bit. You may have always 1, or always 0, or always 1. Yeah. So basically, there are 4 options. What can happen to a bit? It kind of makes sense because if you're not very good in Boolean logic, if you look at all functions on one element, there are only 4 functions on 4 elements. Yeah. Again, let's say so if you have number x, maybe 0 or 1. Yeah. So let's look at function f at fx. No, there are only 4 options what bits can be in for. So again, any function of one argument can be described by 2 Boolean values. Yeah? For example, if I have function which returns 0 and 0, it's a function always 0. So this special name for this function always returns 0. Yeah? I may have function 1 and 1, its function returns always 1. I may have function 0, 1, it's just function x. and I make 5, 1, 0. It's functional text. So there are 4 different things you can do with single bit. Okay. Okay. If you didn't think about it before, you can spend some time thinking about it. If you have single bit, yeah, it may have 2 possible values. Yeah. For every possible value, you may do one of 2 things. Yes, you may turn it to 0 or turn it to 1. Yeah. So I have 2 bits. With every bit, I can do two operations. Yeah. So number of possible functions is like 2 power 2. Okay, let's just short introduction to Boolean logic. Applying logic gates. You may think about logic gates. Logic gates, I think it's kind of harder to visualize. And it's easier to think about just functions, not gates. Yeah, just think about Boolean functions. So Boolean functions of four Boolean functions of one argument. And here are all 4 of them. So again, what you're doing? So all bits actually will be split like in 4 groups. Yeah, some bits always turn to 1, some bits always turn to 0, some bits stay the same, and some bits need to be changed. So let's just split all these bits in these groups. Now, how to build the final program? So I have my initial number. Yeah. So again, so it's like n minus 1. I have 10 bits. Okay, I have 10 bits. A9, A8, and so on. A1, A0. So you look at these bits. So some of them must be zeros in the end. So I need to turn some bits to zeros. Yeah. So I take these bits. So how to make the bit equal to 0? No, you end it with special mask that turns this element to zeros. So you make all elements 1 except the ones you want to turn to zeros. And 1. So let's have more. So you put again, you make a special mask that you have zeros in the places that you want to be zeros in the end. Then if you calculate bitwise end of your number with this mask, then these bits will be zeros, and these bits will not change. Again, because 0 and something is always 0, and 1 and something is x. Okay, again, if you see it for the first time, it's fine. So you just after solving a few problems about bitwise numbers and Boolean logic, it will be much easier for you. So not like we applied. So to first line using one input of B3 and now you apply these operations one by one. So you have your initial number, then apply first operation, apply second operation. So you have a sequence of operations. You take the first operation, take the output of this operation, apply second operation, and so on. So you just have sequence of operations applied. Now we need some bits we need to be ones in the end. So some bits need to be ones. So again, you to make the bit equal to 1, you do like we did in this example. So we have OR and just put in this mask these bits equal to 1 and all other bits equal to 0. So these bits I want to be 1, so I make them 1 in this mask. All other bits I make zeros. So this operation makes some bits equal to 1 or to 0, be 0, and this operation makes some bits equal to 1. And finally, you need to flip some bits. So some bits you need to flip. So for example, you have no A7. You flip the bit by applying XOR operation. So you calculate this XOR again and calculate bit 1 here. You here just flip the operations. Let's just implement this. So okay. So do we have time? Do we have time? We have time. Let's just solve the problem. So let's just write the code. So I have n for so what I will do, I will calculate the state of each bit. State of each bit will be 2-bit numbers. Okay, this is state. State. So I have 10 bits. Okay, you can do it using integer types. Just store them in bits. I will store it like this for simplicity. Okay, so it will be more visual. So state will say. I overcomplicate problem to be it more visual. Okay, so it's code will be much interesting, much easier if I do it easy. Okay. Sorry, that's not how I normally program this problem. Okay, I will just use bit magic to do this, but I wanna avoid it. Let's say f0 0. So here I will remember what will happen to this bit. What will happen to this bit if I apply all my operations and the initial value was 0, or if the initial value was 1. Okay, so for each bit I will remember what will happen to this bit if I start from value 1 and if I start from value 0. Now let's read this. If okay, syntax. Now I will split my x into bits. Let's note how you normally do it. Okay, we will simplify it later, just to show you how simple it can be. So I need to extract bit from the number. You extract bit by doing like this. You have I, pop x, move it to the right by I bits, and end with null. Here I extract 1 bit from the element. Okay. I move it to the right, then make end with 1. So I extract only 1 bit. Now, if I have OR, then I will do everything 0. So let's do it like this. I overcomplicate intentionally. We will improve it. Okay, let's. So if I have 1, then both f0i and f1i should be equal to 1. Now if s equals to, and well, let's say with zeros. And if it is XOR, Then I flip the bits. Yeah. That's all. Basically, I calculate what happens to every bit. So if I have OR operation, I do it like this. Oh. Okay, let's even simplify it like this. So I just apply this operation to this number. I for therefore I x of f I or xi. Okay, and with one. It does the same. Okay? So if again if you OR with some bit, if this bit is 0, you do nothing. If it is 1, you make 1. So these two parts actually do the same. I'll change everything. Do it like this. Okay. So basically, I simply apply all the operations to all my bits and see what's happening in the end. Now, in the end, I will apply 3 operations. First, I will make all bits zeros, which should be zeros. So I'll always make 3 operations, right? Because I can. So if element always should be 0, I will add 0. Okay, so I need to make this bit equal to 0. And if not, can you invert? Okay, thank you. So if at least one of them is not 0, I will put 1 in this position. That's how you set bit to 1. Yeah. So I move one I positions to the left and then calculate bit with OR. Yeah. So it's number x plus this 1 bit. OR x. Now in the same way I will find all elements that equals to 1. It's 1 and this equals to 1 and calculate end. And finally I will calculate XOR. XOR I'll apply if I need to flip this bit. So if 0 equals to 1 and this equals to 0, then I need to flip this bit. Okay, this operation just do nothing. And 0 looks scary. Why should I end 0? No. Or no. Here. Okay. So here when I work or I set up once. So if they are both ones. Sorry, I'm not accurate enough. That's more like it. XOR 1 is. I can't write this program from the first try. What's happening to me? Okay, that was kind of embarrassing. I thought I can write this program from the first try, but again. Bum, 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 bum. Okay, that's because I overcomplicate my own code. So really, this program was what? Oh, that's so embarrassing. Let me see. Why? And freeze doesn't look okay. And freeze doesn't look good. Yeah, I agree. And free kind of looks strange. Okay, you can see even I'm not ideal. Okay, so it happens. Let's see really fast. So pom 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 pom. We read. We check. Why I have this end free? What? So I write and for all bits here. If at least one of them is 0. If this is 0. Oh, fuck. Why? Okay. It's copy-paste problem. Okay. So initial number is not specific. Okay. Oh. Okay, I like this problem even less now. So I need to optimize it like this. Oh. Okay, I don't like this problem. I don't like this problem anymore. Okay, what's the problem here? I thought it's actually easy problem. The problem here I'm trying to apply. Let's look at this test again. I'm trying to apply this expression and I know the problem is here. What? I don't understand. Is it non-negative integer? I don't understand. If this number is better. Can you find the bug? Sorry, it's embarrassing. Word. So this word looks not good. What? And why it's wrong? Why it's wrong? Not my day. Okay, sorry. Sure. Okay, so it's okay. So number x is always 10. Okay, we're working in 10 bits arithmetics. Okay, good. Finally. Now Actually, one of the reasons why I failed is because this program is overcomplicated. So let's simplify it really quick. Do we have time? We have time for it. Okay. Let's simplify it. So what I'm doing here, I work with 10-bit vectors. So every vector contains actually bits. So instead of having vector of 10 bits, I will just use integer. So I will put all zeros in this vector, all ones in this vector. Or ones is useless, like this. Or you can do it like this. Yeah. If you want to have n bits, okay. So this vector contains all zeros, this contains all ones. Here, instead of having this again, vector of elements, I will just use number x. I use number as a vector of bits. I don't need this, I don't need this. Here, I need to apply operation OR to all bits. So instead of using this for loop, I will just apply this operation directly. So I'll have f0 equal f0 or x, f1 equals 1 or x. Bam. Same here, same here. Probably it will be even better to have array of 2 elements. So instead of having 2 variables, when it's 2, it's actually not that bad. But if you have more than 2, if you have f0, f1, f2, I will make array of 3 elements here. Instead of having 2 variables, I will have array of size 2. Yeah. Then you have less copy paste, less bugs. Okay, that's all. That's how we simplify all this code. So instead of having vectors, we just have integers. Each integer is just vector of bits. Here, what I need to do, I need to find all elements that equals 1 in both f0 and f1. Yeah, I'll just erase it. So I need to find elements which are equal 1 in both f0 and f1. So and x actually just equals to f0 and f1. Same here. I need to find all elements which are ones in at least one of them. So instead of doing this, I will do it like this. And finally here. So I need to find elements which equal ones. So f0 equals 1 and f1 equals 0. You do it like this. So f0 must be equal to 1 and f1 must equal to 0, like this. So again, I just apply all this operation to all bits. This operation I apply to all bits. Instead of all this stuff. Let's just inline this up. Can I inline? That's all. So this the same program, but just simplified. So just by using bit magic instead of all these vectors, I just simplified my program. So it does the same, but it's faster than the previous one. It does use vectors. It just use numbers. But what's more important, it's easier to understand. Yeah. So it looks like doing some bit magic will make your program less understandable, but usually it's not. Usually, if you know how bit operations works, by using them actually makes your problem easily understandable than just without them. And actually, time is actually pretty much the same. So okay. So it's not that fast because yeah. It's just it's just not very slow code. Any more questions about this bit magic? If you bet the bit magic, just solve few problem which involves bit magic. It's not that difficult. Yeah. So this operation applies AND to all bits. This operation applies OR to all bits. This operation applies XOR to all bits. Yeah. Just try to understand what happens when you AND to some mask, what's happened when you OR with some mask, what happens with you XOR with some mask. Problem F is pretty standard problem. You need to find some subset of integers with given sum. So it's well-known problem actually. No, sometimes if you don't have this, so you need to calculate, so you need to be divisible by m. So you need to sum equal to 0 modulo m. There are different variations of the problem. In the most classical variation, you need to find sum of problem equals to m. Yeah. So here I need to be divisible by m. In the most classical variation, you need to find sum equals to n. And it's like one of the variations of the knapsack problem. Knapsack problem is known to be NP hard, but for small elements like here, if I have, if you have m to the power 3, so if all elements are integer and are small elements, and if your elements are small integers, it can be solved using dynamic programming. And the way you do it, so if you don't know how to solve knapsack problem, you definitely need to learn how to do it. I will not explain it a lot, but just shortly explain. How you solve knapsack problem is by maintaining like dynamic programming array. So like the of x. Is it possible to have some like boolean? Can I have some equal to x? So basically maintain an array of Boolean variables. For each value, you maintain Boolean if you can have this sum or not. Yeah. And then every time you pick an element, you update all this sum. You take all this sum and take from some x. So you take some element from your array, so like ai. Yeah. And you move from some x to some x plus ai. Yeah. So you either take this element or you don't take this element. If you don't take this element, your sum is the same. If you take this element, your sum is here. Okay? So you apply both these operations, update your dynamic programming. In the end, you have, for each sum, you know if you have this sum or not. If you calculate, if you want to have it divisible by m, it's basically the same, but here you need to calculate it modulo m. So basically, for each remainder modulo m, you remember if it is achievable or not. You have Boolean value. Can I have a sum of some elements equal to this number modulo m? That's all. Interesting thing, now it's okay. This is all standard. So this is normal knapsack problem. If you never solve knapsack problem, just find the contest about knapsack problem and solve it. So I have a lecture about knapsack problem. Pretty standard. What's interesting? Interesting what happened next. Because here the constraints are like solution of knapsack problem have time complexity nm. And for these constraints it's too much. So it will not pass the tests. So you need to have some idea how to improve it. And okay, there are multiple ways to do it actually. The most interesting way I think is to think what is the worst case for this problem. So worst case is when I have a lot of elements, yeah? But this sum m is small. So in the worst case I have a lot of elements. And I need to have at least some divisible by small number of m. And it looks like if you have a lot of elements, it should be kind of easy to find set with which is divisible by m for any constant m. Yeah? Like imagine you have m equals to 2. Yeah, and you have like a million of elements. Yeah, you have a lot of elements. It looks like it's easy to find some divisible by 2. If I have some even element, at least one, I can take this one element. And if I have odd elements, 3 and 5, I can take any pair of odd elements, and I have something divisible by 2. So if number m is much smaller than number of elements, it looks like it's always easy to find the set which is divisible by m. And it's actually turns out to be true. So if n is at least m, there is always a set which is divisible by m. Why is it true? No, easiest explanation is like this. So if you look at sequence of your elements and look at all the prefix sums. So look at prefix sum, including empty. So you have n plus 1 prefix sums. If you calculate these prefix sums modulo m, you have n possible values. So two of these prefix sums should be the same modulo m. For example, this should be like, I used s, and this prefix sum is also s. So two prefix sum have the same value s. And if you have this, then the segment between them should be divisible by m. So if you have the same remainder modulo m here and here, then sum on this segment should be divisible by m. That's all. Actually, can you just use it using knapsack using bit magic? Probably can. Yeah, I think you can just use. Okay. Probably you can just use bit array instead of normal arrays, and just apply this operation. And 10 power 6 should be enough. Maybe you can just using bit array knapsack. But that's easier. That's easier. So again, the solution is like this. You see that you have some knapsack problem. And you think, okay, this knapsack problem, I know how to solve it in n-time complexity. What's next? So you can just implement it, see it works, and then see that you have time limit. Then you think, what should I do with this time limit? And think, okay, what can I do? I can do something like this. So what is the worst case for my solution? It is test when I have a lot of elements like this. But maybe if I have a lot of elements, is there an easier way to find the good set? No, it actually turns out it actually is. That's how I think in this type of problems. So again, you get some solution, it doesn't work on some tests. You think, okay, what I'm doing when I have tests like this and solve problem with tests like this, maybe you have some another test, then you think, what will I do in this case? You kind of have solution and you want to try to find the worst case for your current solution and think, what will you do with this type of tests? And after a couple of iterations, you kind of, sometimes it happens, so you are out of bad tests. If you don't see any bad test for your current solution, then probably there is no. Okay. Let's look at your solutions. We have two problems more. Okay. Let's look. Pum, 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 pum. Why not? Plus 10 is just to be sure. Okay. I love when you add this plus constant. I also do it like this sometimes when I'm not sure. Yeah, it's just safety measure. During the contest, it's fine. When you are judge, you're writing judge solution. You don't do it like this. Yes, but during the contest, perfectly fine to add some random constants in perfect place just to be sure that you have enough. Okay. But yeah, and that's normal knapsack problem. Yeah. So we have this array of booleans. Yeah, yes. Yes, and I believe you can do it using bit array and it will be just fine. Good. Two problems left. Let's go. Problem G. Nice problem. It's actually quite standard problem for dynamic programming. It's not standard, a little bit standard in the end when you try to implement it. But again, the setup is very typical for dynamic programming problems. So what we have here, we have some strange process. In this program, we have some writing lifts. So we start at floor A, and we do some writes. Yeah, and we need when we do these writes, we write down the floors we're visiting, and we need to find number of sequences. No, basically you calculate number of different paths you can make. So if you write down the floors you visited, you have some path basically. Yeah, and you need to calculate number of different paths. That's what's happening. So after you understand what's going on here, so you have some strange basically graph of these floors, and you need to calculate number of paths in this graph. When you can, yes, so you can travel between floor using some rules. So here you explain how this rules works. Quite typical. So when you want, so first of all, when you calculate something modulo prime, like here, so you need to calculate number of some objects modulo prime. 90% time you have some dynamic programming. Another 10% when you have some combinatoric formulas. Sometimes it also happens. So you have some factorial, some stuff like this. It may be some combinatorics, but most commonly it is some dynamic programming, like in this case. And like here, so again, problem looks very standard for dynamic programming. We have some strange graph. Size is not that large. Yeah, so these numbers are small. If you have 10 power 18 here, then probably you need some combinatorics here. If you have like 10, that you have thousands, 10 of thousands, it's probably just some dynamic programming. So if number of, how to check if it is dynamic programming or not? You look at number of states. If number of states is relatively small, then it's fine, yeah? Like in this case. So what is the state? State is how many trips I make and what floor I'm currently in. Number of trips is at most k, number of floors is at most n, yeah? So total number of states is like n multiplied by k is like 25 millions. Not that much, yeah? 25 millions even fit in the memory, so you can make array of size 25 millions. So looks promising, okay? So it looks like problem for dynamic programming. Then what do? You just implement dynamic programming. Let me. I actually done it yesterday, so I can just show you my solution. Let's do it like this, so I don't spend that much time. It will be a little bit less interactive, but let me just show you. I spoiled you. Okay, I spoiled you the outcome. No, okay, let's go. Let me show. So this is basically how dynamic programming usually looks like. Some people make just two-dimensional array here. So here, instead of, I usually do it like this because I'm used to do it, but again, up to you. So what I'm doing here, I have one-dimensional array and another one-dimensional array. And every time I apply one more element, I move from my current state to the new state. And then in the end, I just swap these arrays. You can swap them and clear if you optimize. I usually don't optimize until I get time limit. So if you have time limit exceeded, then you try to optimize. It's usually optimizing before you get time limit. It's not beneficial. So what I'm doing here? So what this state? The state count just number of possible paths that ends in this vertex. So for each in this floor, so for each floor, I found number of ways I can stand in this floor, and then you apply the next trip, and you move from a current floor to another floor, and you recalculate this dynamic programming and so on. So what I'm doing here, so this is my initial state. I can stand in any floor with one possible. No, I cannot stand with floor B, so you can say db equals 0. But it will be 0 anyways in the end, so it doesn't matter. Now, what I'm doing here, I create a new array D. Yeah, so there will be number of ways I can get to this state after one more step, after one more right and left. And here I just apply simple naming programs. I check all my floors, all next floors. Now just apply this constraint is directly from the problem statement. So let's go back to the problem statement. Back to the problem statement. Yeah. So you just this constraint. Yeah. It's exactly here. I just rewrite it. So I can write to any floor except x if this distance is less than this distance, like here. So I have not anything intellectual here. Basically, I just applied normal, pretty standard dynamic programming. Nothing actually interesting happened here. Very standard dynamic programming. Here I calculate modulo mod. You can calculate it right here. I just calculate in the end because I can. Doesn't matter much. That's all. So you apply one step, then move to this next step, and you can apply it again, apply again. In the end, output what you need to apply. I'm doing it from the end. Where the A. A is starting. Okay, I'm doing it in the reverse order. That doesn't matter. So again, that's basically the solution. And now when you submit the solution, if you submit, I would not submit it, but I don't have. So in real context, I would not submit the solution because I know it will time limit. It will time limit. Why will it time limit? No, because if you calculate carefully what I have here, I have 3 loops basically. No, it's easy to calculate time complexity when you have 3 nested loops. Yeah, I have k, n, so it's k multiplied by n square, and all numbers are up to 5,000, so it's 5,000 square or cube. 5,000 cube, it's too much. Yeah, so it will time limit. So how you improve it? There are several ways, standard ways how you improve dynamic programming. You can improve dynamic programming by just reducing number of states. Sometimes you have too many states. So you just think that some of these parameters are not important. In my case, all parameters are important. I have just 2 parameters, and basically number of moves and and my current floor, and they kind of both look important. Yeah. So I have like k multiplied by n states, and it looks like all of them are useful. Yeah. Or you can improve the time complexity of recalculating a single state. So here I basically iterate for all states. Yeah. But this loop used to calculate this one value. So to calculate single value, I need to make this loop. So I need to make n operations to calculate a single element of my dynamic programming. Yeah, so maybe this actually can be improved. It turns out, yes, it can be improved. So you look at this loop. So what does it make? What does it do? So it calculates sum here. So I calculate sum of all elements of some elements dy. Yeah, and if you look closely, all these good elements belong to some segment. So. So you have element x, you have element b. Let's move closer. Not b. So you can move to all elements. So this distance is less than this distance. Yeah. So you have this distance d, and you're interested in all elements in this region. So basically you need to calculate sum of all elements in this segment except element x. So basically what we're doing in this loop, in this the most nested loop, in this loop, we calculate sum in some segment of array D. No, you can calculate sum in a segment of array using prefix sums. Yeah. So instead of calculating these normal sums, I will calculate all prefix sums. Then I calculate this sum minus this sum, and this sum minus this sum. Or I calculate total sum minus this element x. Also works. So using prefix sums, I can replace this loop with a simple subtraction of one prefix sum from another prefix sum. And this loop will be eliminated. Instead of this loop, I will have just constant time computation of this element. Clear enough? So again, there are a few steps in this problem. First step is understanding what's going on and seeing that you have something like a good setup for some dynamic programming. Then you write a dynamic programming. You cannot implement like this. You can just write it on paper, just all these formulas. Then, after you build your dynamic programming, you see it is too slow. Yeah, so time complexity is like 5,000 cube. It's too much. So you need to improve time complexity. You think, what can I improve with the time complexity? And usually you improve one of two things: number of states or time you use for calculation. Number of states, it's hard. It looks like number of states cannot be decreased. So I need all this n multiplied by k states. So let's try to improve time you need to calculate a single state. And you look at this calculation, see this calculation can be performed using prefix sums, apply prefix sums, get n square solution, and you won. Okay. Let's look at my solution again. So this is the same. So this is the same solution. We choose prefix sums. So I have array D and I have array of prefix sums here. Here, every time I calculate prefix sums, and here instead of the second loop, I calculate left and right border of my prefix sum and calculate prefix sum minus prefix sum, and I subtract element dx. So I calculate sum on this segment minus element dx. Yeah. So again, I do these operations instead of this nested loop. And now I have good time complexity, and now it works. Boom, 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 boom. No questions. Good. Let's look at your submissions. Who was the first? Oh, yes, you just use prefix sum here. Okay, you have you actually have special setup for prefix sums. Okay. No, why not? No, here you calculate get L. What is? You use it to calculate left and right border of your segment. Makes sense. And subtract this element. Plus mod because if it is negative, because you subtract something. Yeah, makes sense. Last problem is actually again pretty standard problem. It's called a minimal superstring problem. So it's quite again, it's a well-known problem for a long time. So what we have some number of strings, and we need to find shortest string which contains all of them as a substrings. That's well-studied problem. So it is NP complete. Obviously, not obviously, but again, it is NP hard. To find the shortest possible superstring is NP hard problem. It's not a trivial, but again, it is NP hard problem. But here I have only free strings. Yes. So important thing, I have just free strings. So for free strings, finding the shortest possible superstring is actually not that hard. So how do we construct superstrings? No? We do it like this. Let's look. So you have some S1 is doing you can call them okay, X, Y, and Z. Y, okay. So let's look at the answer. So we have this answer. In this answer, we have somewhere have string S1, S2, and S3. Yeah. If some characters of the resulting string do not are not inside one of these strings, so like this, I don't need them. So I can remove all these characters, all these characters, all these characters. Yeah. So all the characters of the resulting string must belong to one of these three substrings. Makes sense, right? Yeah. So let's remove everything not necessary. Now, if one string is completely inside another substring like this, then let's just remove this substring S2 from the set. Yeah. So if I have substring S1 in the set, substring S2 also will be in this as a substring. Yes. So if one of the substring is, if one of these three strings is a substring of another string, I can remove it from the set. Now, let's look at the order of the substring. So we have S1, S2, S3 like this. So you have the first substring, the second substring. So let's sort them by the starting time here. So the starting time of the next should be somewhere here and should be like this. So the second string can be completely inside because I removed all the substrings. Yeah. So it must be somewhere like here. So it may have some intersection here, or it may be empty, or it may be like this. So if these two strings intersect, this string must. So what I want to say, if you sort all the strings by the left border here, the right border will also be sorted. Yeah. And that means that okay. So what I want to say that the result always looks like this. So my resulting string always looks somehow like this. And if it looks like something like this, the total length will be sum of all these lengths minus these two things, because I calculate them twice. So the resulting string will be sum of these lengths minus length of these intersections. And now you want to just find the maximal intersection of two strings. Maximal intersection of two strings is just maximal suffix of one string equal to prefix of another string. Yeah. So what I will do, I will check all the possible orderings of these two strings. So I have like 3 factorial, like 6 possible orderings of these strings. So you put one string, let's say alpha, and then second string like beta, and then like gamma, like this. And then you find the maximal possible intersection between alpha and beta, maximal possible intersection between beta and gamma. Yeah. And calculate maximum sum over all possible permutations of these 3 elements. How to calculate maximal possible intersection? No, it's not that easy actually. So if you never did it before, you need some string algorithms. Again, if you don't know any string algorithm, learn at least one. Okay, there are possible things. There is Knut-Morris-Pratt algorithm. There is Z algorithm, and there are hashes. Basically, that's all. Usually, you need at least one of them. Like in this problem, any of these algorithms should work. I recommend to learn all 3 of them because it may be easier for some problems to use one or another. Yeah, so they're not the same. Hashes are in fact usually more universal, but they are it's hashes, so it's random. Plus you have some. It's usually too slow. It involves some modular arithmetic, so it's slow. These algorithms are faster than hashes, and they don't involve any randomness. So if you can use something, if you can solve something without hashes, it's better to use solve without hashes. So how to how to, for example, find this intersection using KMP? No, you can do it like this. So you have alpha and beta. So yeah. So you have string alpha, you have string beta. I wanna have a suffix of alpha here equal to some prefix of beta. How you do it using KMP? No, you concatenate these strings like this. You concatenate them beta, then some special character, then alpha. And then calculate KMP of this. And KMP calculates something called prefix function. So it basically calculates maximal prefix equal to suffix. And that's exactly what I need. I need maximal prefix of beta equals to suffix alpha. So you concatenate them, then run KMP, and it will calculate you this. Easy. Same thing with Z algorithm. Z algorithm calculates something different, calculates Z function, but it basically works in the same way for this problem. So Z algorithm find you the maximal string starting from this position, which is equal to prefix. So you do the same thing, then find this position. So from this position, this suffix should be equal to this prefix. Or you may use hashes. So you just check all possible suffixes, all possible prefixes, check if they're equal using hashes. Also doable. So again, there are 3 possible ways how to solve problems like this. I actually really recommend to learn all 3 of them. I have a lecture about this, just you can watch it, and it's not that hard. So all these 3 algorithms are very easy actually. So just learn all of them and just apply them when you see that you need them, like in this problem. Any questions? Let's read your solutions, because I didn't have my solutions. So let's read one of your solutions. Actually, a lot of people solve this problem. That's good. It means you not only know these algorithms, you also know how to apply them. Oh, contained. I use hashes. Okay. Yes, you also need function which checks if one string is substring of another string. Yes. Oh, that's nice. So you just iterate all possible permutations of 3 elements by hand. It's not bad. I would do it also like this. You can use, like in C++, you can use next permutation for this. Also perfectly fine. But if for 3 elements, you can just iterate them by hand. You need to be careful. Sometimes you make bugs when you do it like this. But if you believe in yourself, it's nice. For 4 elements, I would definitely write loop. For 3 elements, good enough. What is prefix size? No, again, so we use hashes. Okay. So if you have the same, okay. No, you just check all the prefixes, check they're equal. Yeah. And you reverse the string somehow, right? No? You did like this, okay. Okay. Because for prefix size, I thought you reverse one of the strings, so you have 2 prefixes. Good. Anyone used KMP or is it hashes? Oh, Z function. Oh, nice. Well, you just show you that it's actually much easier to use something. So you don't have all this modular magic. You don't have these strange constants, strange hashes, and so on. It's pretty simple. So again, do all the same thing. Yeah, that's the whole algorithm of calculating that function. It's actually that short. Can you do it even shorter? No, it's fine. It's actually a pretty nice implementation. So that's the whole algorithm that calculates that array. And then you basically use it. You use next permutation. Good. Even for 3 elements, it's nice to use that permutation. Next permutation, yeah. Extend. Why not? So basically add strings one by one. Nice. In here you check if it is already a substring, you just skip it. Nice solution. Okay, so again, the final problem actually required some algorithms. So I believe it's the first time in this series when we had something that requires some special algorithms. String algorithms, one of the so when you learn algorithms, it may be one of the first thing you actually can learn. They are easy. No, okay, they are not that easy. Okay, they're easy to implement. Let's say so. Implementation of all the string algorithms is pretty short. Both KMP and Z algorithm and hashes, they all have very short implementation. So after you understand what's going on, it's quite easy to learn how to do it and how to use it. No, it's again hashes. Okay. Okay, so everybody uses hashes except one. Okay. No. Oh, what prefix function? Okay, we have one that uses. We have one uses Z algorithm, one who uses KMP. So prefix function basically it's Knut-Morris-Pratt algorithm. Yeah, so we calculate prefix function. It's that short. So that's the whole implementation of Knut-Morris-Pratt algorithm. So it's again just if you never try it, just try to learn it. It's not that hard. It's okay. The logic behind this prefix sum is not that trivial, but the algorithm itself, that's the whole code. Yes, and here we just apply. So again, it's not that hard problem, but it involves some algorithmic knowledge. Yeah. Okay, so thanks everyone. See you next time. Tomorrow I will post next contest. So see you next week.